Okay, now you already understand the application for spray combustion in different kinds of practical application. Now we start to learn the spray frame structures, and as you remember, basically for the gas phase, for the gas combustion, we try to identify two different category of burning structure. One is the so-called premise frame. The other one is the diffusion frame based on the boundary condition, or we call initial condition. If initially the fuel and the oxygen they are separate, then the burning structure will be described based on the diffusion frame, because the diffusion frame will separate the fuel supply and the oxygen supply in different regions. They meet together, the fuel and the oxygen meet together just at the diffusion frame positions. But for premix fan, we understand the fuel and the oxygen they premix together before they reach to the flame surface, and we call this as a premix flame. Similar way, we can identify the spray flame structure as the spray diffusion flame or spray premix flame based on the liquid sprays and the oxygen you may have. If you mix the spray with the air initially, and then you will produce the spray premise flame as we described for liquid aqua engines. But you separate the liquid fuel from the air, and they will have interaction, but on the interface between the fuel spray and the air, then all the combustion will occur in the interface of liquid spray and air. By this way, fuel separate with oxygen by the flame, by the spray boundary, or we call it by the spray flames. Then we call this the spray diffusion flame. Let's talk about the spray diffusion flame as first, and then later on we will move to some discussions on the spray premise flame. There is a several discussions on different spray structures to let you know how the spray diffusion flames characteristics. And the first one you can figure out here, there is the three different kinds of spray flame, right? And those spray flames depends on the spray atomization. The left-hand side, the first one they tell you this is a poor spray atomization. How can I say the poor spray atomization? That means that those kinds of mechanisms provide a spray with the large droplet size. That means that if you have many large droplet size, the evaporation gasification strength will be reduced. They need more time to gasify to become a vapor, right? Then the droplet will retain their liquid phase to a longer distance. Okay. For example, this is the first case. In this first case, they tell you we can generate a spray with the larger droplet size. Okay, those droplets and those droplets, large droplets will exist in the interior of your whole spray cone under evaporation process, and continuously they will completely gasify. When they complete gasify, that means that they will have a lot of fuel vapor accumulate inside of the flame. Okay, by this kinds of structure, you can figure out that the whole spray, actually, they are surrounded by a diffusion flame, and those diffusion flame basically supported by the vapor coming out from the spray core, because they are they have a very dense spray here, large droplet size accumulate in these regions. They can evaporate, they produce a certain amount of fuel vapor, and those fuel vapor will come out, diffuse out to mix with oxygens. Then they will generate a flame. This is a diffusion flame, and this diffusion flame will attach to the spray boundary. Okay, if you have a spray here, and they produce a certain fuel vapor out, and those fuel vapor will meet with oxygen from outside, then they generate diffusion flame. Usually, this diffusion flame will very close to the spray boundary. Okay. And in the large region of this diffusion flame, in this the interiors, they contains many fuel vapors to support the outer diffusion frame. But when you go to the downstream side, since those the droplets is already they spend more time because droplets large, and here they will evaporate completely as the fuel vapor. All those kinds of evaporation or gasification basically by the heat from the outer diffusion frame. Okay, and later on in this downstream region, you may have the so-called the purely gaseous diffusion frame, and those diffusion frames just burn the fuel vapor and oxygen in the downstream sites. Okay, this is a typical spray frame you may have. In this case, the major feature for the spray is it contains a very large droplet size in the spray region. And the next one, you try to produce droplet size become more tiny, and but they may show you some extension, something like this. In this case, for this case, the spray they still have a larger of the liquid coming out, but with the more small droplets, but they will extend to a further distance. In this sense, here they still have a few vapor evaporate. If you those droplet size large enough, they can move to the further downstream sites, and those evaporation persist to the downstreams. Then they can still produce a few vapor to support the outer diffusion frame. Then you can see there is the spray frame. There is a spray frame extended to the very far downstream. Later on, you may have some droplets coming out because the droplet size becomes small, but they do not have too many. And in this case, a spray frame shrinks to a small area. The droplet coming out to mix with oxygen burn as a single droplet. Okay. The difference between these two spray frames actually you can figure out is for this one spray they may have a many large droplets. Since if you have a large droplet, then they will extend to a longer distance. The main spray frame structures mainly is completely controlled by the outer spray frame. Okay, those we say this is a box spray frame. Actually, is supported by the fuel vapors. Okay, and they, in the interior of the spray, they contains so many droplets. And since the initial droplet size is large, then those kinds of droplets with the large density and also a number density and a large droplet size, then they can extend longer to make the whole diffusion frame controlled by the fuel vapor coming out from the interior of the spray. Okay, but the left hand side tell you may have some droplet exist and large enough, but maybe the number density is not too many. They will evaporate soon in a certain region. Later on, the outer diffusion frame generally is supported by the fuel vapor left in the interior of spray, but in the interior of the spray, actually they do not have a droplet size exist. They do not have a droplet exist, but just a fuel vapor. Okay. And the second one, the third one is when you have you may have some droplet coming out, and they have a very strong mixing with the outer air, and you just have a small region of your diffusion frame and support by the fuel vapor gasified from the liquids. Later on, the droplet size becomes smaller. The oxygen penetrations into your spray region with a well mix, then they will separate the droplet to different kinds of small area. And just like burn in the downstream side, there is a small region as a diffusion frame surrounds a group of droplets, or sometimes you will have so many tiny droplets burning. Okay, these are three different kinds of spray burning structure you may have. Generally, if you look at those kinds of spray frames, you may have a spray code from the cold flow observations, and you will have a spray cone, right? Usually in the vicinity of an injector, the sprays already have some atomization, but usually they still have a large amount of liquid exist. Then those kinds of gasification is weak. They produce just just small amount of fuel vapor coming out, which means that those fuel vapor coming out to support the surrounding diffusion flame. Basically, we majorly they are controlled by the spray. Okay, this is a spray diffusion flame, but those diffusion basically is the gaseous phase, gas phase combustion, right? Your fuel vapor burning with the oxygen. Okay, but those diffusion flame extend further. Later on, you will find out in the lower region, in the upstream regions, the interior of your diffusion flame contains a certain amount of liquid drop. Okay, but when you move to the downstream more, in different kinds of spray characteristics, you have a well atomized, uh, uh, well atomizations, the evaporation complete very fast, very easily. Then in the downstream side, you still have a large fuel vapor exist. Then in this region, the outer diffusion flame basically is mainly supported by fuel vapor only. But for this case, the interior of your spray flame still contains certain amount of liquid fuel, okay, liquid drop, okay. And later on, if this liquid drop is large enough in the downstream side, they will burn as just an individual droplet diffusion flame like this, or maybe an island of a diffusion flame surrounds and in the interior of these islands contains a group of droplets inside of the diffusion flame. And I want to give you the more understanding about the diffusion flame structures for next slide by introducing the famous so-called group combustion theory. Uh, those proposed by Professor Chu. Uh, he was the chairman in IAA in our university. And this is a very famous so-called group combustion theory. The main idea is this. When you think about the spray flame, as we described in previous slides, you may have a spray structure like this. Okay, now let me explain how can we have a flame exist depends on the equilibrium ratio you will have, right? For example, can we have a flame exist? You need to think about how much fuel you have, how much oxygen you have, and if they have enough, if the ratio between the fuel and the oxygen is exists in the flame limit, that means that you may have a flame exist, right? Now try to think about how kinds of flame you may have in those different kinds of locations for given spray. Okay, look at the spray from the left hand side. You have a spray coming in, right? And those liquid jets similar to the gaseous jets. Initially, we will have a so-called potential cone corresponding the gaseous flow. Okay, and since if you have a well designed for your flow structures in this region for the gas flows, you can maintain the potential core, which means the actual velocity is equal to the injection velocity of the gas phase flow. Now spray coming out, then here they show you a lot of droplet individual presents. Here we try to eliminate the so-called the liquid sheet. Okay, here maybe you may have a liquid sheet, but they try to give you the overall structures. You may have a so many droplets exist in this spray cone. Actually, by this kinds of illustration, tell you we treat this as the so-called solid cone, not a full cone, the solid cone or full cone, not a hollow cone. Hollow cone will restrict your droplets, liquid droplet in the layer of the spray, right, of the cone. Now, we try to evaluate the concentration of the fuel and the oxygen in different locations and to justify is it burning or not burning, okay? and the identification can be viewed from the top the figures. Here, this figure tell you the horizontal axis represent the percentage of oxygen you may have at that locations, and the vertical axis represent the percentage of fuel you may have in that locations. Now we try to examine their situation at different locations. For first one, X1 here, actually X1 is near the center line of the spray, right? Definitely you understand in this region you do not have too much oxygen, but you have a lot of fuel here, even they are as a liquid droplets. Now you can plot that points at certain position in this plot here. This is one means you have a very large percentage of fuel but has a less oxygen. In this situation, they are very rich without enough oxygen. Then you do not have a flame exist. Then we call this region is a so-called extinction. Extinction means that you may not have a flame at the position of 1. Okay, now you understand the situation at position 1. We try to move your position to the boundary of your spray. When you move to the X2, you realize when you move X1 to X2, actually you move your position from the dense region to the more dilute region, right? The region near the spray boundary, actually they tell you the droplet size becomes smaller, and they have a more possibility to let air penetrate into the interior spray. Then X2 for the fuel concentration, actually they tell you still rich, but oxygen concentration increased, but still not enough for produce the sprayable flame. Actually, X2 in this region, we just have the so-called fuel, the evaporation of your droplets. Okay, but when you move to the X3, the boundary, near the boundary of spray, now you may have enough oxygen. The position shift to the position 3 here. Okay, the left-hand side, there is the undetermined region, but separates the extinction and the stable flame. Okay, and extinction means no flame exists for position 1 and 2, but for position 3, they tell you a possibility, the concentration distributions for fuel and oxygen to let you have opportunity to have a spray flame, the diffusion flame stabilized here. Okay, then you can see if you consider this as a spray, right? Then you may have a spray flame surrounds the spray cone. Okay, definitely you will figure out here in this boundary you can have some fuel vapor supply from the droplet gasification. Then the emit oxygen that will generate the diffusion flame exists here. Okay, and they give you an idea, and they say the so-called external group combustion. What is the meaning of external group combustion? External means the burning occurs in the surrounding of your spray cone. Okay, it's outside of the spray cone, and there is a group combustion means they got a few vapor coming from the evaporation of group of the liquid droplets in the interior of spray. Okay, here those big group of droplets, they evaporate and produce a fuel vapor. Those fuel vapor will diffuse out to mix oxygen to produce the burning at the boundary of your spray. Then we call this the so-called external group combustion. Okay. Now we move to the a little bit downstream side to look at the positions 4 and position 5. Position 4 is still very close to the axisymmetric line of your drop spray. Definitely, you believe the fuel concentration is still high. The position here is still high. Oxygen is still not enough. Then we do not have a flame exist here. Then you try to move to the boundary of your spray to X5. Okay, it is good because the oxygen concentration increased, but not enough. You do not have a flame here. But when you move further to the outer boundary, you will reach to the so-called X6. Okay, X6 means in this region you have more oxygen coming in, And here in this region, x5 to x6 means now at this position x5, you already produced some fuel vapor coming out, and the droplet size becomes smaller, and the space for the distance between the droplets become larger. That means that you may have a more oxygen penetrate into your spray field. Those situations will give you some idea about you may have a so-called X6, X6 here. You will have a stable frame. This stable frame arranged is a cover at this boundary, and inside of this frame, you may have a group of small droplets enveloped by a small diffusion frame. Okay, now we call this, we move to the so-called the internal group combustion. Internal group combustion means you have a group of liquid droplets, okay, but the diffusion frame penetrate into the crop of the droplet and stabilize inside of the spray boundary, and then those a small group of liquid droplets surrounded by this diffusion frame. Okay, and this we call the internal group combustion. Internal means diffusion frame shrink into the spray boundary. Okay, here I want to expand a little bit why for external group combustion, the spray frame is exists in the outer boundary of your spray, because those fuel vapor and the spray is very dense. Okay, they do not have a large separation distance between droplets. The oxygen cannot penetrate in. Therefore, in this region, you can treat it just like you contain so many liquid here, oxygen cannot penetrate in. But in this region, oxygen can penetrate into the spray, because in this area, the spray is dilute. Dilute means the droplets has a large separation distance, allows oxygen coming in. If you have air, oxygen coming in, then they will generate a small spray frame, and this spray frame cover just a small group of droplets. Okay, that means that your diffusion frame shrinks into your spray boundary. There is a spray boundary. Okay, you can see this, you can say this is a spray boundary, because the definition for the spray boundary means in this within this boundary you have many tiny droplets. Okay, this is spray boundary. But the diffusion frame penetrates into the spray boundary, then generates a diffusion frame and burning a group of small droplets, and we call this as an internal group combustion. You go further to the X7, X8, and X9. Actually, they will give you, for example, X7, 9, X7, and 8. The percentage of fuel becomes smaller, oxygen become larger, because the droplet size becomes smaller. Okay, oxygen can penetrate in, but they still accumulate a certain high amount of fuel vapor. Then we may not have a flame exist here. But when you move to the X5 or further downstream in these regions, yeah, this just happened. There is some internal group combustion exists. Finally, when you go further to the downstream or into the outer region, in the downstream region, you will find out you do not have a droplet depth, because all droplets under high temperature environment, they will completely evaporate. They just have a few vapor left. If you just have a few vapor left in this region, that means you will produce the diffusion burning. Okay, but this diffusion burning mainly controlled by gas phase combustion. Okay, and we call this as a turbulent blast flame exist. Okay. And this is a typical spray structures considering the flame existence. And you can see from the upstream side to the downstream sides, and 2 points. The first point you can figure out the liquid spray generate droplet, right? Droplet initially has a larger size, and they will move from the left-hand side to the downstream right-hand side. Droplet size reduce continuously, even diminish in the far downstream side. In this process, the liquid will be gasified, produce some vapor, and later on continues provide the vapor. You can see the initial regions those vapor will support the outer diffusion frame by the balance with the diffusion, the supply of oxygen from outside. And later on, when you move to the further downstream, you will find out the spray condition become more dilute, more space to allow oxygen can penetrate into the spray cone. Then the outer diffusion frame has has its motion to penetrate into the spray boundary to envelop a certain group, a group of a certain small tiny droplet as a burning, like internal group combustion. And in the upstream side, basically the burning exists in the outer surrounding. Then they say we say this is an external group combustion. Okay. When you look at the distribution of your liquid droplet from the large droplets and the more dense situation, then go move to the small droplet size and dilute situations, then you can see the structure change. The oxygen can penetrate into the spray region to make a good mixing. Then the combustion behavior will change from the external group combustion to the internal group combustion, and later individual droplet combustion, and finally is the turbulent brush frame. Okay, this is we look at the whole process based on the fuel atomization and the gasification process. And along this process, the second point is the diffusion of oxygen from the air into the spray cone. Initially, they stop on the periphery of the spray boundary, right? Because they cannot penetrate into this dense spray region. But when you move to the downstream side, the spray situation become more dilute, more space, then your oxygen can penetrate into the spray cone. Then you can have good mixings to produce a local internal group combustion behavior. Okay. Now, this is a very good introduction to let you know the combustion structure accompanied with the atomization of your liquids. Now, we try to give you the slightly descriptions on individual external individual group combustion features. Okay, and this is a typical explanation to let you know the relationship here. Okay, this actually this is still the same figures, and we took it from the Professor Chu published in Combustion Science and Technology in 1977. Okay, here you can see there is a potential cone I mentioned earlier. Now those dots represent the droplets under evaporations, and here you can see this is outer diffusion frames. Okay, we call this as the external group combustion, but external group combustion can be separated as two kinds of group combustion. External group combustion. One is the so-called external shape group combustion, and the other one is the group combustion. I will explain a little bit later to identify the differences between these two models. And we move to the internal group combustion here. In internal group combustion here, they tell you there is the spray boundary, right? This is the outer boundary. It contains all the droplets inside, and then we call this a spray boundary. But now the diffusion frame already penetrates into the spray core, and inside of the diffusion frame, those droplets actually they under gasification evaporation only. But when you have a diffusion flame pass through the droplets, those droplets will be ignited to change their gasification process from evaporation to burning, right? Then you can see there is so many tiny droplet burning exist. This is one of the example for the internal group combustion. This is typically, as I mentioned here, there is a flame surrounds a group of droplets, okay, and there is also have an outer spray boundary here, and we call this as an internal group combustion model. If you move to the further downstream, since the droplet size, separation distance between droplet becomes smaller, even smaller, then they do not have enough fuel vapor support the diffusion frame. This diffusion will move to the interior, the center region, and to finish it, all the ignition, then you finally we will have a single droplet combustion in somewhere here, and later on you just provide the fuel vapor to support to support the diffusion frame. We will go to the turbulent brush frame. Okay, let's look at a little bit descriptions on individual group combustion model. The first one, we focus on the external shape combustion. What is the meaning of external shape combustion? This model can be built, observed by these descriptions. Here, the external shape combustion means there is a spray boundary. Okay, here there is a spray boundary. All the droplets exist in this in the interiors of a spray core, and outside in the outside surroundings we have a external frame. Okay, this is a back diffusion frame. And the most important thing is you realize the diffusion frame is basically support by the fuel vapor coming out from the spray core, right? Okay, definitely you understand the fuel vapor will be consumed with the oxygen coming in, and most of them will be consumed completely at the position of the back diffusion frame. But the main definition for external shape combustion shape means those fuel vapor coming from the a layer of the droplets, okay, in the outer layer of your spray cone, okay, which means here inside of your the interiors of a spray cone actually do not have too much evaporation, because in these regions is very close to the injector, right? This region basically the spray is very cold, temperature is low, the evaporation process do not have too much. The strength is very weak. Therefore, the interior, the center region, in the center region, all the droplets do not have too much gasification. But the layer, the outer layer of a spray cone, experience the heat coming from the flame, they will start to evaporate, and it provides the fuel vapor to support the outer flame. Okay, now that means that in this case, for your spray, you just only have a layer of a droplet to evaporate to support the fuel vapor for the diffusion flame. Then we call this the external shape combustion. Okay. But you can figure out this mode will change when you move from the exit of injector to further to maybe for these regions. Since when you move to these regions, the environment for your droplet become more hotter. When you have more hotter, that means the evaporation will extend. The evaporation of liquid droplet will extend from the boundary, spray boundary, to the interior. That means that all the liquids droplets inside of your spray cone will provide the vapor. Then we call this is the group combustion, external group combustion. Okay, the differences between the external shape combustion with the external group combustion, the difference is for the shape combustion means the fuel vapor supply only a layer of droplets in the outer layer of your spray cone. But for external group combustion means all the droplets start to evaporate. They provide the vapor for the outer diffusion frame. That means that the fuel vapor support a supply coming from all the droplets inside of fuel vapor of your spray. But for shape combustion, they just got the fuel vapor supply from the outer layer of a spray cone. Both of them relate to the so-called external group combustion. Okay, this is the first explanations for the differences. Yeah, actually, you can see by compare these two figures. The left-hand side tell you the external shape group combustion, right? There is the outer layer of spray cone. Inside inside this in this layer, all the droplet evaporate. But the center core, they do not have evaporation. They show you the non-vaporizing droplet cloud. Okay, and there is a layer, outer layer represent the vaporizing droplet layer. But those kinds of vaporization for the droplet will extend to the all droplets. Okay, together they totally support the fuel vapor to for the diffusion burning. Then we call this as an external group combustion. And this is the basic difference between the shape combustion and the external group combustion. Okay. Now you try to figure out now the all the definition basically depend on the fuel vapor supply, right? And oxygen penetration. If they change because when you move from the upstream to the downstreams, actual fuel vapor supply will change continuously, and they have more room to let the oxygen penetrate in. Those kinds of characters to balance to have a position for the diffusion flame. Now you can figure out for the next step, you go to the further downstream. In the downstream side here, okay, initially the fuel vapor coming from the spray cone, they will support the diffusion flame, right? But later on, when you go to the downstream side, the fuel vapor the coming out become less. That means that the diffusion flame, the outer diffusion will have a possibility try to move to closer to your spray cone, right? And limit the spray, the diffusion flame will attach to the spray boundary. Now you can figure out later on if the fuel vapor is still not enough to support the outer diffusion flame, then this diffusion will shrink into the spray core. Okay, this is the behavior. Now your diffusion flame here, the bulk diffusion flame exists here, but the boundary of your spray cone is like here. Okay, the limiting case, the diffusion flame just attached to the spray flame, to the spray cone boundary. Now we already have some additional step. Now the diffusion flame move into the spray cone. They represent two important combustion characteristics. The bulk diffusion flames envelope a group or a cloud of a droplet, and this diffusion flame basically is supported by the fuel vapor coming out from this group, this cloud of of droplet. Okay, but outer regions they have some single droplet exists, a single droplet burning exists. Okay, then we call this so-called internal group combustion. The group combustion behavior exists the interior of your droplet or of your spray cone. That means that we call this as a internal group combustion. Okay, and you can figure out to move to the further downstream of your spray. Droplet separation increased, fuel vapor reduced because you some of the vapor already consumed. You do not have too many liquid droplet to support enough fuel vapor to maintain your diffusion positions, diffusion flame position. Those diffusion flame will shrink to the center and disappear those bulk burning structures, and you will not have a bulk diffusion flame. Then you just have an individual droplet burning exists somewhere here. Then we go to the so-called single droplet combustion model. Okay, and later on, all the droplets finish their gasification. Only fuel vapor left in the very far downstream. Then finally, you just have a turbulent brush flame. Turbulent brush flame is purely gaseous flame exists in your downstream. Usually, in that situation, the burning is more relative to the turbulent premise flame because the fuel vapor is already has a good chance to mix with oxygen, where in the downstream the burn just like a premise flame situation. Now you understand those kinds of combustion features by looking at the different position for the spray atomization. And Professor Chu tried to give you a number, try to identify how much number how much you have a number, then identify different kinds of combustion features. Here, from the lecture notes, actually, you can see this plot. The horizontal axis represents S. X you can refer to the some non-dimensional value, but basically they try to give you the understand S represent the non-dimensional separation distance between droplets, the separation distance between droplets. Right? S smaller s means the droplet has a small distance. That means in that region is belong to the so-called dense region, right? When you have a larger separation distance, means the droplet has they will separate for a large distance. Then in this region, we call this a dilute spray. Then simply you can see in this region, this is a dilute dense spray region, and this region is the dilute spray region. The other one, the vertical axis represent the total number of droplets for given volume. That means for given control volume, and you try to evaluate the number of droplets. That means that you are thinking about the number density. Okay. Now, if you have a small value of n, that means that in this control volume, you have a small amount of droplet number. That means that you do not have too many droplets in this region actually corresponding to the dilute spread. Similar way, you can see if n is small, corresponding to small s here. I'm sorry, I should say if you consider the small n and the large s here in this region, the right bottom corner in this region, they tell you the droplet separation distance large and the number is a small. Number is small. That means that in this control volume, basically is purely dilute. Okay, it's very dilute. Okay, but for the top left corner, tell you now you have a large number of n and with a small separation distance. Then they will tell you the meaning on this region, the field is very dense. Okay. And this is the meaning for the N and the S for this plot. Additionally, Professor Chu, they proposed a so-called group combustion number, try to group the N and the S together by this way, N to the power of 2/3 divided by S, and this is a group combustion number. Now you try to figure about this. For if you have a large N and a small s, then G will be increased, right? What is the meaning of large N? Large N, that means that in this control volume, you have so many droplets, okay? Accompanied with small s. You have many droplets, that means the separation distance will become shorter, okay? And large N, small s, both of them will give you large group combustion number and represent very dense spray, okay? And which means in this corner, okay? For example, there is the boundary that tell you this G equal to 100, okay? If the G number higher than 100, that means that all the spray is very dense. In this situation, you will figure out where is this position. Actually, it's very close to the spray injector, right? It's a dense region. In these dense regions, you may have a so-called external shape combustion because it is so dense. The center region of your spray cone is very the temperature is cold, is low. They do not have a chance to have a very effective evaporation. Only a layer of the droplets in the outer layer of the spray cone, they will start to evaporate, produce a certain fuel vapor to support the outer diffusion flame. And this is a typical typical external shape combustion we already introduced. Okay. Here they tell you if you look at the fuel vapor contributions from the center to the outer boundary of your spray cone, they tell you the contribution basically coming from the outer layer of your spray cone. Okay, there is almost no evaporation occurs in the interior region of your spray cone. Okay, And this is a typical examples for external shell combustion. Now you try to reduce the G. What is the meaning of the reducing G? Reducing G means that you reduce the N, the number of your droplet in the control volume, right? Or increase the separation distance. Actually, you try to move the spray situation from the dense to be slightly dilute, okay? And you have a slightly dilute, actually, you move your position, your observation from the vicinity of the injector to the downstream side one by one, step by step. You will move from the external shape combustion to external group combustion. In these situations, the G number between 1 to 100 in these regions, okay, now the outer bulk diffusion flame will be supported by the fuel vapor evaporate from the old droplets inside of your spray cone, okay. Later, you decrease the G number more, then the spray become more dilute. In this case, the outer diffusion flames do not have enough fuel vapor coming out from the spray cone. They have a possibility to penetrate into your spray cloud. Then the bulk diffusion flame exists inside of your spray cone, okay, and the outer region of your spray of your diffusion flame will exhibit several individual droplet burning. Okay, and you reduce the group combustion number further. Then you go to the very dilute sprays. Then you may have a single drop burning exists in the whole combustion field. Okay, and later on you the older droplet disappear. Then you move to the turbulent premise flame or turbulent blast flame. Okay. Now we use this part to bring in the parameter of G to give you the understanding for spray conditions from the dense spray to the dilute spray. Actually, we try to move our observation from the vicinity of the jet of the injector to the very far downstream, and you can see the spray characteristic change. Then the combustion behavior will change continuous from shell combustion to the external group combustion to the internal group combustion. Then later on, you will have a single droplet combustion. After all, you will have turbine brush flame. And this is a very nice explanation for the possibility of different kinds of spray diffusion flame you may experience. But definitely, those kinds of modes may not exist for all kinds of sprays. Depends on the spray atomization is good enough, or they have some different kinds of feature. Those kinds of burning may change, may not include all the modes in a single spray flame.